So yeah, so what sort of background do you have to get into corrosion there, Kyra?
Oh, I don't know. I did my PhD on polymers,
Polymers.
and catalysts, to be fair.
You weren't possibly trying to make biodegradable polymers, were you? And you moved over to metals as a fulfillment of that.
Well, actually, so I was breaking down polymers using a metal catalyst. So then I kind of and using different solvents, and that's where I sort of realized that the interplay of like what's happening in the system is far more interesting than just sort of tweaking one little variable to get it to do a specific. So it's kind of like learning how the environment can drive something to happen or not happen. But I guess, yeah, I started to like inorganic chemistry and liked how metals behaved. And so there you go. Same principles apply. It's just a slightly different way of thinking about it.
And so, yeah, so what was your first degree?
In chemical engineering from MIT.
Okay. And when was that roughly?
Is this to age me, John? I got my bachelor's in 2008.
2008. Yeah. Okay. Very good. And I mean, just sort of putting it there, you then went to Imperial after that.
Cambridge.
And then, I mean, how different did you find the US and UK university systems?
I think at the different levels, they're quite different. I think Cambridge is a little bit anomalous, having watched the undergrad experience there. So I think that's kind of like, you kind of have to keep it as a separate entity. But it is quite different. It's different how we examine students. It's different in that sense in particular for undergraduate level, but also chemical engineering as a discipline is very different in the US than outside the US. So it's much more chemistry based in the US. At a PhD level, the UK really encourages independence. And I think that's reflected in lots of sort of historical things and how things are structured. But yeah, they're different places. There's lots of differences. There's lots of similarities. I'm not sure one is better than the other.
And do you think you might go back to the States? I'm not trying to get rid of you, but I'm just curious.
Oh, I don't know. It's less bad than it was. No, we're very happy in Sheffield. We love Sheffield. I've gone full circle. I grew up in a steel town in the US called Cleveland. And so I've moved to a steel city in the UK, Sheffield. So I feel like, we've closed the loop. But I love it in Sheffield, John, but you know that.
Both of them are ex-steel as well, I guess.
But Kyra, how can you say that Cambridge is anomalous? It's the standard university in the world from my experience.
Oh, I don't know. My husband and I usually jest about which one is better. MIT is obviously superior to Cambridge.
Yeah, okay. Time out, guys. Take this one personally offline.
Sounds like a plan.
Got to move quickly here. So you started out. So you've done your PhD, and then you're looking at corrosion. I mean, do people take this seriously? Do you think corrosion gets the attention it deserves?
No, that's like the whole ethos of what I'm going to try to sell today to everybody who has thought they would listen. I thought to myself when Kyra said how many people come, I was like, oh, the number will be lower because corrosion was in the title, and nobody will want to hear about that. The tagline at the very end is that actually this is a real problem, and it's a problem in every single industry. Mm-hmm. So, but also it's a huge problem for nascent technologies where we're using solvents that we're not familiar with. And we don't have years of experience to basically take from a database what might be a good idea in terms of ensuring safety. So the problem in some ways is momentous, and we're less willing to take risks that people took a long time ago. So the challenges are actually quite significant, but it's not a particularly popular topic. It doesn't seem to inspire, like it doesn't have that kind of cachet. It doesn't have that sort of, oh, you're going to get on the cover of a journal, you get into this, everyone cares, but it's the thing that's going to make stuff happen safely.
Yeah.
And I really care about deploying new technologies and technologies that are going to make the world a better place, a more sustainable place. So if this is part of how we get there, even if everybody else thinks what I do is boring, if I'm going to help us get there, then so be it.
Yeah, I think there is actually, at the moment anyway, quite a lot of tendency to want to always try and do something new rather than making sure we can do what we need to do, but do it.
Yep.
That seems very common. Anyway, Kyra, please go ahead and tell us what you wanted to tell us, and then hopefully we'll have time for some animated discussion.
Fantastic. Thanks, John. So I think hopefully everybody got to know a little bit about me, and you can all see a little bit about my personality. So I probably prepared too many slides. I will be the very first person to admit that. And I'll try to go through them kind of quickly so that there is time for discussion. And my goal today is to make you care about the problem. It's not necessarily to tell you about every nitty-gritty detail or provide you with a 30-minute summary of, a review paper. But I want you to think about, I wanted to sort of get everybody thinking about the problem. And I want to talk to you a little bit about what I foresee is how we can actually develop a solution in reasonable time. How we can be effective, how we can make this happen. And so that's kind of the focus of my talk. Now, for this audience, I don't need to tell you the motivation, right? I don't need to tell you why this matters. But I do want to kind of roll back for 1 second and just talk about the piece I'm going to focus on. But I want to highlight that this isn't isolated. So we all know about the process, that it's not isolated just to CO2 capture, and I'm going to focus on post-combustion capture. But corrosion is a problem that is pretty much ubiquitous to a wide variety of the technologies. And the truth is that, as I just said when I was chatting with John, that realistically speaking, corrosion is a problem in every industry. There's not an industry that doesn't have a corrosion problem. The question is just how serious it is and how well controlled it is. And so when I'm talking today about post-combustion, I'm talking about it for a range of reasons. But I want you to keep in mind the fact that things like CO2 transport pipelines, this is a major issue. This isn't just isolated. So, what is holding us back from realizing post-combustion capture? And I'm probably not the person to debate whether or not post-combustion capture is the answer for every technology and that sort of thing. And as I said, the concepts I'm going to talk about today can actually be applied more widely. But if we take it as sort of a standard for right now, is what is holding us back? And two major factors, which are really closely interlinked, are financing and corrosion. And the reality is you're probably thinking to yourself, well, financing has lots of aspects. It has, CapEx, OpEx, and these sorts of things. And why is she saying that corrosion is intimately linked? And actually, I'm gonna kind of come back to that at the very end, and I hope you'll be able to see that thread winding through. But the issue with corrosion is that corrosion is one of the reasons we make decisions about infrastructure materials. So what we build a plant out of is influenced by what we believe we need to ensure the security, safety of the facility. And so depending on what you pick, it's going to cost a different amount. So there's your CapEx. And then as corrosion occurs, we have to have monitoring, as well as things like downtime management, etc. So these are all going to fold into your OpEx. So why should you care about corrosion? Because it's an influential factor in all the key financial decisions. It doesn't mean that there aren't other important factors, but it is one of the major players. So what's holding us back is the problem that we don't really understand what's causing corrosion in general. There have been a range of academic work in terms of studying post-combustion capture and its impact on corrosion. But compared to the literature looking at other aspects of this process, corrosion is minuscule, right? It's a minuscule component of the area. And maybe that's because up until recently, right, people didn't view the viability of it actually happening. I don't know, maybe we're all being cynical. Or maybe we were willing to accept a high level of risk. But the reality is that we have a range of variables which impact corrosion. And I've listed a few of them here on the slide. You can go and find in literature some various, mostly lab-based studies that look at different aspects like temperature, solution chemistry, flue gas chemistry, operating conditions, infrastructure, materials even are addressed, but none of them are sort of comprehensive, right? They all look at kind of these trends and they all look at a reasonably set of isolated conditions. And I'm the first one to hold up my hand and honestly say that I'm part of that group, right? That I'm part of the group that hasn't yet been able to put together what I would consider a really holistic, comprehensive study. And part of the reason is there isn't much appetite to fund it. So what do? We're all taking bite-sized chunks out, and some of that collectively can be brought together, but it's leaving some gaping holes. And that's a really big problem from my vantage point. So the other thing, before I sort of highlight a little bit about the risk aspect of the problem, is that there's this constant discussion about corrosion and solvent degradation and how they're interlinked. And often corrosion is blamed for solvent degradation, but sometimes solvent degradation is blamed for corrosion. And the truth is the two are basically in the same pot, right? They're both creating things that are encouraging one another to happen. And the result is they're negatively influencing one another. They're basically two bad actors, and they're encouraging each other to continue to do bad things. So this adds another sort of complexity. And if we go back and think about finance, risk, management of the system, you start to see how corrosion is basically an unavoidable problem that we have to figure out, in effect, how we're going to manage it. The risks, I harped on about financial, but ironically, right, financial pales in comparison at the end of the day to doing additional environmental damage. But also, I mean, let's be honest, number one concern is health and safety of people working in the facility, people nearby the facility. And some has-up analyses have been done. I took a quote from a Polish paper, a paper with a team of Polish authors, and I say that because I'm not going to embarrass myself and try to pronounce their name. I'm really sorry. But there are almost no has-up analyses on the topic, right? And there's this it's very limited, but they do highlight that this is something we need to be considering. And so it's really nice to see it out there. To see somebody actually saying we need to be worrying about this problem. This is not a negligible issue to realizing this technology. So I'm going to try to move to a more positive view. I'm going to try to move away from a negative viewpoint, and I'm going to think about how we can manage our risks, because I'm a realist. Corrosion is not going away. There is not a magic alloy that is going to stop it from happening, and certainly not a magic alloy that is within the price point that this technology can afford. It's just not there. So instead, we need a viewpoint, which is how do we manage our risks? How do we reduce our risk to a tolerable level? And my answer is that we need to understand better what's causing the corrosion. And we use that understanding, we're going to funnel that back. And that's going to put us in a position where we can start making educated decisions. We can start making better choices based on that information. And I recognize that corrosion is not a problem in isolation, right? You can't pick these specific criteria because they reduce corrosion, because if the process isn't effective, then you're not doing what you need to do. So it is an optimization problem at the end of the day, but the corrosion side of it, we need to sort of find a way to manage it better. And we need to gain a better understanding of how we are going to manage it. And so, from a scientific point of view, understanding is what is going to lead us to doing that. Otherwise, the risk we have is that all our choices are based on false assumptions. They're based on simplifications. They're based on, sort of incorrect knowledge. And that's a really risky position to be in. And my personal view is that if we want people to adopt this technology, we need them to believe in we don't just need them to believe in its ability to deliver. We need people to believe it's safe. We need people to understand that it's financially viable, and we're doing our best to make the best decisions. We can't afford to be wasteful, and we can't afford to make a mistake, because that will taint the entire operation, right? Globally, from the point of view that people will then become very wary. So how can we reduce these? Solvent selection, process modifications, material selection, flue gas treatment, more. There are lots of options. Those are kind of the big headers. So where do we come in, right? As scientists, engineers, be it in academia or in industry? And the answer is that we range across we go all the way from the lab into what we want to be, which is a large scale industrial facility. And, you know, pilot finds itself happily in the middle. So the question is, how can we understand better and solve corrosion problems better? And so in the lab, right, we can conduct immersion studies. So these are still basically the gold standard in corrosion. They're ASTM standards that we tend to follow, and they allow us to basically look at net mass loss, which is basically a way, if I can pull up my pointer here, I don't know, but we look here at net mass loss as a way of basically telling us how much material we're losing. Now, I would go further and say that you actually want to look at the whole system, and you want to understand what's happening in the entirety of the system. That's how you understand the driving force behind what's causing the corrosion. So whilst, you know, this is still a gold standard method, and mass loss is really what people are going to represent. That's what they tell you. This is how many millimeters per year you're going to lose. That's useful in terms of understanding what we're losing, but it doesn't tell us what's causing it, how it's causing it, what's happening, all of the parameters that go into this happening. So, you know, as an academic, I'm looking at a broader spectrum, but recognizing that in industry, that's not always viable. So where do we go from there? So if I just take a minute and highlight the mass loss issue, because this is it's been around a long time, and there are a lot of limitations to this. And this is part of the reason that, you know, most people who look at corrosion try to look more holistically at what's happening, because the problem is if you represent corrosion rate by a simple equation like the one here, you have lots of sources of error. And those sources of error can very much impact your decision. But the biggest problem is that you assume that you have what's called uniform corrosion. And what uniform corrosion is doing is it's telling you that the corrosion is equal everywhere, that there is nowhere that's sort of deviating from the norm, that you've got the same thing happening. And this can be a valid assumption. In some scenarios, this is what you have. The problem creeps up when this is not what you have. And so you have to be very wary. Now, doing immersion studies is not the only way to study corrosion, right? It was the original method. It is still a very, very standard method. It's an expectation. And to be honest, it gives you a tangible sense of loss. It tells you how much of your material you're going to lose, right? And then you get an idea of, you know, how robust is my infrastructure going to be if I'm losing that many millimeters per year? How often am I going to have to make changes or update it? But there also are a lot of excellent electrochemical methods that can tell you a bit, because corrosion is inherently an electrochemical process in part. And so there are a lot of techniques that are often used to better understand both generalized corrosion and localized, which I'm going to speak about in a minute. So in this short talk today, I'm not going to talk about the electrochemical methods because in and of themselves, that's a lot to discuss. But there are different methods, and they all can give different information, and they can be extremely powerful tools to understand what's happening in your system. So you have a better way of describing the sort of the electrochemical and the chemical reactions which are occurring. So they're very powerful, particularly when used in tandem with kind of an immersion style study where you're looking at what's physically happening to a piece of metal. If you're interested in this, I did a webinar a while ago. This is not to toot my own horn. It's just because I know it's there and I know it's reliable. I have a video you can watch if you want to learn about these different techniques. The application in those videos is more about oil and gas corrosion, but there is a tremendous number of similarities to these applications because it's a lot of CO2 based corrosion. So if I move on, because I'm conscious of time, I gave this really big warning that you need to be thinking about the fact that if somebody tells you you're going to lose this many millimeters per year, you have to be thinking to yourself, well, okay, that's only if it's uniform corrosion, right? So they give me a really low corrosion rate. Does that mean I'm safe? And the answer is maybe, but maybe not. And so one of the things that I personally worry about a lot are localized corrosion phenomena. So even if I'm not observing huge weight loss and I'm not seeing lots of sort of signs of quote traditional corrosion in that sense, I'm constantly thinking about all these different types of localized corrosion that might be occurring. And so this is kind of like I'm going to preface something I'm going to show in a minute, but one of the challenges is that localized corrosion can often be very, very catastrophic. If it's not tended to, it can be quite surprising. It can happen very fast, but it's harder to detect. But it also can happen in lots of like high alloys. So it can happen in those materials you paid a lot more for. So that's sort of that really expensive stainless steel could exhibit localized corrosion and could have a failure. And so this is where decisions get really, really complicated in terms of how do you make a good choice, right? Do you want to choose the material that's kind of corroding uniformly but slowly, predictably, or do you want to go with the material that's more expensive and really should be looks more resilient, but some lab indications show that it could be sensitized and you could be ending up, for example, with some aspects of localized corrosion? Then it's going to come up, you know, how do you make those choices? And these choices are not trivial. And I think anybody working with systems where there isn't a tremendous amount of historical data struggles with how you make a really good decision in these types of cases. So I'm prefacing, right, this idea that you're going to have to make material selection. And that's how I started, right? I said money. This is all about money. Are you going to buy the cheap steel or are you going to buy the stainless steel? And so where this starts to feed into is what happens, not just in our sort of controlled lab environment, but what happens in a pilot scale. And then in a minute, I'm going to comment on what do you have happens when we scale up and we can only sort of implement monitoring. We have to use the knowledge we've gained. So in a pilot scale, we've got massive challenges because we don't have the same control over our system, but we also have a much more real environment. Where there are fluctuations, where there are changes, where in effect, things are less perfect. And so we may have more difficulty stratifying our data and figuring out exactly what the parameter is that's controlling the corrosion, but we may also get a much more realistic sense about performance. I suppose in the, you know, the common sort of everything's talking about is this is the difference between a clinical trial and looking at real world studies. You know, you have this discrepancy. And so I picked out an example, and I just want to be open and clear that, you know, I've just picked one. This is from the CSIRO group, published their results from their Terang facility with MEA in 2013, and I picked it as an example, but there are lots of other great examples out there. And they basically recognized what I'm getting at, which is this idea that essentially, do you need a more expensive steel or do you need a cheaper steel? So they wanted to assess it on a pilot scale at a range of points to kind of understand whether or not you needed to make that decision. And so they looked at basically two cheaper steels, a 1018 and a galvanized 1018. And then they compared it to two expensive steels, a 316L and a variant on that. And they looked at them at all these different sites to basically get a feel for the difference. And one of the things you can see, so here I've shown the examples of the 1018 and the galvanized 1018, is that even to the untrained eye, you can see that this metal is damaged, right? From being in the system, it's been damaged. And that's not always a deal breaker, to be entirely transparent, right? That may not be a problem, but the reality is we need more information. So an example to kind of highlight this in a different way is to show you, so they looked at, you know, how much was the corrosion rate comparatively. So in the graph on your left, they've got their cheaper carbon steels, and on the graph on the right, they've got stainless steels. And what you can see is that basically the order of magnitude of corrosion rate on the x-axis is 2 orders of magnitude larger for the carbon steels than the stainless steels. So based on their method, which was a gravimetric style method based on the ASTM standard, they saw an enormous amount more, quote, corrosion than in the carbon steel than the stainless steel. And this continues to be true when they looked at 3 sites on the stripper. And in fact, the problem becomes even more exorbitant, right? We're now talking close to 3 orders of magnitude in some of the cases. So the question then is the stainless steel better or not, right? The carbon steel is undergoing a more predictable phenomenon. And the stainless steel, on the other hand, we're always worrying about that localized corrosion phenomena. So on the surface, the corrosion rate looks great. And to their credit, right, they've commented on some observations of localized corrosion. But that's where it gets murky, right? So which one do you choose? And this is where we need to think about the feedback, right? Feeding back to the lab and working together, and actually sort of piecing together this information to try to better understand what is going to be the life cycle. So what happens is that we have this lab data, right? And I talked about different ways we can collect data, but it's in a very constrained circumstance. Then we've got pilot data, which is less constrained. But the thing is that, you know, it's much more real world, right? We have a real sense of what's happening. And so for those who have an industrial facility, you can't always just have these coupons in, looking at how much deterioration you have. And so we look at online monitoring methods. And so again, there's not too many examples of this in the literature, although these are well-established techniques that are used in things like natural gas sweetening. But there is an example that TNO's published in 2015 and talked about this, where they put the probe down there at the bottom, which is one place they'd identified in their system as being particularly problematic. To be fair, most people have identified that as being a particularly problematic spot for a lot of reasons. But they've looked at it and they're using it to gain information and basically looking at the idea of, can you monitor adequately in these types of systems? And is that reflective of what's actually going on if we look at corrosion coupons? So we are already thinking, and there are groups thinking about how you're going to make this translation. But one of the challenges in making this translation is we're still in a position where we don't know a lot about the system and what's happening. And so it's still somewhat risky. And I think everybody would like to de-risk the situation as much as possible. So what can I do? And the answer is, well, most of the work I do is in the lab. And I think about the system and the different regions and what happens, but I'm coming back to what changes can we actually make realistically, and what concerns do I have about what choices of material we're going to build with, and what can I do to make the system more compatible with the infrastructure material so that it's possible, recognizing that probably process modifications are limited. Flue gas treatment may not always be possible. So I need to be prepared with a whole host of solutions. And so in 1996, TOMO basically was one of the first groups to identify that the type of amine employed was actually the chemistry of the amine was impacting the corrosion that you would observe. And this was a really important seminal sort of change in the view. There was a little bit of work by DuPont in the early 90s from a natural gas sweetening perspective that kind of laid the foundation for TOMO to do this. But what was really exciting, is it still is exciting about the paper, right, was highlighting this link. And that kind of kicked off an acknowledgement that there was a problem. And this was followed, and you know, there's not very many groups working on this, but VOAB and the group in Regina have also done some work where they also continued to show in the late 90s and early 2000s that basically amine selection would significantly impact the corrosion you observed. And I said I wouldn't talk a lot about electrochemistry, so I've included the graphic from their paper, but I'm not going to get into the nitty gritty. But what you can see, right, is that it's self-consistent. We've got an issue where the amines are not behaving the same way. And my own group has looked into aspects of this as well, albeit quite a bit later, and we're very grateful. I'm grateful to all those who came before me and who started sort of developing the chemistry behind it. And in my case, what you're looking at here on the graph is looking at the iron-ion concentration in the solution, because I was using that as a slightly different way of doing real-time monitoring to better understand what the kinetics are, what's happening in terms of the loss of the material in real time. But what you can quickly see is that, first of all, you've got I've shown two different graphs, right? So the graph on your left has basically losses of iron ions much higher than the solutions in the graph on the right. And so what that comes down to is chemistry yet again. We're talking about the chemistry of the amine, and that's the result, is that what's happening. So I'm going to describe that a little bit to those of you who are not familiar. And I'm going to start with the tertiary amines, because through indirect capture, but because of natural gas sweetening, these were actually studied more early on by people like DuPont. But what they discovered was basically that you had iron carbonate formation. So here you can see an image taken by my group, where you can see crystals forming on the surface, and the crystals are forming as a result of the fact that you have basically iron ions combining with carbonate, bicarbonate, etc. And you're growing these crystals on the surface, protecting it. So you don't see the same amount of iron ions in solution because your iron ions are being consumed for the most part, forming those crystals. And to some extent, those crystals are forming a barrier that's going to protect your iron or iron-based substrate against further oxidation. And so in this graphic, this is an example with piperazine, but you can see the crystals forming in figures A and D. And what you can see in B and E is actually the layer itself. So through a cross-section taken, you can actually see here, so this one is 9 plus or minus 1 micron, and the one on the bottom is 8 plus or minus 1 micron. You can actually see that layer is pretty significant. On top of it is just some epoxy holding it down. So the question becomes, though, is that layer actually protective? Is that layer actually passive? And passive is a dangerous word in corrosion because that means that there is literally no continuing reaction. So getting that is sort of like reaching infinity. But we have the further problem that we don't have consistent crystal formation. So the crystals that form, so how they nucleate and how they grow, is very much impacted by the nature of the solution. So now we're back to sort of core fundamental science, which is what is causing the crystals to form and grow, and is the shape they grow, the size they grow to, their ability to dissolve, their robustness against certain things. How does that impact their ability to be protective? And you can see an example of this that I've taken comparing the same substrate at 14 days and at 21 days. You can see the crystals have grown in size, but you can also see the crystals are less well formed in the subsequent measurement. And whether or not that correlates to poor performance in terms of protection is another issue. But what this is showing, right, is that the formation of iron carbonate maybe isn't the solution. It's not immediately clear. And to be entirely fair, iron carbonate formation is something that's been widely studied in oil and gas industry. It's something that I study in oil and gas applications and remains a subject of great debate about the topics I'm just mentioning. So I think saying that iron carbonate, i.e. siderite, is the solution is very risky business. It doesn't mean that it won't be useful, but it means that it's not a panacea. But what can we do? Well, I mean, this is something that my group is working on, and we're working on using advanced techniques, including electrochemistry, QCM, and synchrotron experiments to better understand this. And maybe we will be lucky and we will be able to form a layer that's super protective, but we're not necessarily holding out hope just yet. The other thing, I guess, is that I just talked about MDEA, and I think everyone in the audience would agree that we're not going to have a solvent that's just MDEA at this point, that's not very likely. And I know if nobody else, John will certainly say that he's a fan of MEA, and we should all get on board. And I certainly won't sit here and disagree with him. But MEA's got a lot of challenges, even if it is the industrial solvent. But if you all play along with me for the next few minutes, and you sort of accept that maybe we need to think about how we're going to deploy MEA, the problem we have is through the direct capture mechanism is it corrodes steel, mainly steel substrates like carbon steel. So we don't get that same mechanism where we grow that lovely siderite. Instead, we get just continuous oxidation. So what's happening during that process? Well, initially, this is kind of what our system looks like, where we've got ferrite, which is kind of what we would expect. Our metal sample looks clean. We've got kind of nice status quo before starting, and then very, very quickly the situation deteriorates. It doesn't take long. You can see from these optical microscopy images as well as just the photographs, it does not take long for the coupon to be damaged. But I think hopefully everybody's gotten the message that I've sent to you, which is, okay, but we don't rush to judgment, right? We don't rush to judgment. Is it possible that in fact, this is not a terrible thing? Maybe it's, well enough, we can predict it. If it's uniform, okay, that's a plus. But simultaneously, is it, maybe is it protected? The answer is no. So before rushing to judgment, we can make all these sort of, concessions. Realistically, outlook's not great. In 1 week, you can already see, the cementite inside the coupon. So that means that the labile iron ions from the ferrate are being released preferentially, which means you're exposing the cementite, which basically means you're oxidizing it and you are corroding it in a colloquial sense. So if you missed all of that, all that matters is you can look at the surface and you can look at the SEM image. Look where I've got the blue circle, actually blue oval if we're going to be precise. And you can see that the texture of that surface is quite different. That's because we're starting to expose that cementite iron Fe3C, which is not a good thing. After 5 weeks, you can see lots more of that. You can see lots more of that rough surface. And again, you can start to see its presence in the blue oval, but what you're also starting to see is the presence of oxygen. So the compositions taken on the right are actually sort of approximate EDS data, giving you an idea, a feel for kind of what the composition is. But what you can see is we're starting to form oxides. They could be FeO, Fe2O3, Fe2O3 hydrated. It could be a range of different things. It could also be, it could be changing as a function of taking it out of solution. So XRD confirms these types of formations of these types of crystal structures. But what we start to see as we go on to 10 weeks is the situation is becoming even more egregious, right? That product layer is starting to be removed. So we do still see traces of different types of iron oxide, but realistically, right, we're starting to see some of it also sloughing off. So that's definitely not good. From the point of view that if you're putting iron ions into solution, if you go back and think to that graphic where I said co-conspirators, corrosion and solvent degradation, so you're producing iron ions in 10 weeks. It doesn't take long to up those concentrations to quite significant. And remember, your fluid is cycling around. So all you're doing is you're encouraging more of it to cycle. And so here's kind of, I think a picture says 1,000 words, right? So we did these experiments 1, 5, and 10 weeks, and you can see the product deposited all over the glass surface. So that kind of gives you a sense of how much. And then we were actually able to collect the precipitate. You can see it there, right? So this is what is floating around in your MEA system. This is what you have, which is going to be encouraging along further solvent degradation, particularly the fact that you're going to be sending it all the way through the reboiler. It's everywhere. So we can go back to mass loss, right? I think I've given you a lot of evidence to show you that it's bad. We can go back to mass loss. Here are 4 different ways that we often present it. And one of the things in the bottom right in figure D I've done is highlighted for you where the mass has been recollected. I think this is to give a sense that if we don't look holistically at the entire system, i.e. look at how much is deposited on the surface, how many iron ions you have in solution, you don't get a sense for how the process is occurring. And I think that is a really, really important thing in this particular instance. We need to know what's happening. That's the only chance we have at combating it. So a little schematic for those of you who maybe are struggling to visualize what's happening is that you've got oxidation of iron to iron 2+ in this particular system. And what you can see is that you've got a little bit of product layer formation at week 1. You've got increasing product layer formation at week 5, but you also are starting to see more of that precipitate. And then you're seeing less of the product layer formation as it's delaminating, removing because it's not well adhered, and you've got more on the surface of your vessel. And of course, we're having a reduction in our weight loss, in our weight of our actual coupon as the iron ions continue to be generated as a result of the oxidation process. So we can talk about other metrics. We can talk about understanding the trends, how the iron ions, as you can see after week 5, we're seeing a huge surge, and that very much supports this sort of outlook. But, this is, I have to imagine at this point listening to me, first of all, you're thinking, well, we're doomed. But second of all is thinking, okay, so what do we do about it? Because I always like to see, you see a hill in front of you. the answer is not the hill is too high to surmount. The answer is I can surmount it. The question is how, what tools do I need? And so in traditional, in related systems like natural gas sweetening, but also in lots of other industries, corrosion inhibitors have been the primary solution. And so that's one of the educated changes we can make. And historically, we've got really good evidence that they can work. Here's a, sort of a really short summary. I'll provide the slides after today's talk for anyone who wants to look further into the details. But we have a track record. The problem we have is we have things like vanadium in a lot of our options. So a lot of the choices are not choices we can really make anymore, right? Times have changed. We need to have inhibitors that are green, sustainable, eco-friendly, whatever term you want to put on it. And that has posed another challenge. So somehow that hill is growing, but it doesn't mean we can't solve it. And so there have been a limited number of studies that have been done looking at some different methods for doing it to do corrosion inhibition in these types of systems. And I won't attest that this is comprehensive, but these are, at least a significant proportion of the studies that have been done. And one of the things you can note that I've added parenthetically is I've talked about the mechanism by which the inhibitor is acting. And this is really important because actually this is again about being more targeted and more effective. And so some of these choices that have been made are very much to hit the problem as we know it. And so if we sort of think about the problem as a whole, well, the better we understand the system using a wide range of techniques, including electrochemistry to pinpoint things like anodic and cathodic, the need for an anodic or cathodic inhibitor, the better off we're going to be. And so this is something that, again, my group has been working on. And what I will show you is how we have worked with a copper-based inhibitor. And you can see the dramatic difference. So the system is the same as the one that's been shown here. You can see that there's no deposit on the surface. And then you can see that the coupons all look very, very clean. These are after 10 or 13 weeks. And you can see the great significant distinction. So the addition of a copper carbonate based inhibitor has allowed us to, over the period of 13 weeks, result in no apparent corrosion at this level. So digging in a bit deeper, we don't find any mass change that isn't within the margin of error, regardless of the concentration employed. And what's more, we don't see any iron ions in solution as measured by ICP-MS, regardless again of the concentration we've added. And what's more interesting to me is then saying, okay, well, this does look like it's working, but 13 weeks isn't long enough and we don't have a long enough study. So we can't go into a pilot facility and just dump some copper-based inhibitor in, but what we can do is start to figure out why we think this is happening. And that gives us a fair shot at figuring out whether or not it would be effective across a wide range of conditions. And so I'm pretty much going to leave it at this. This is something that we are working on at the moment and we'll be publishing in the next few months. But what's quite exciting is that we can see that even using UV-Vis, we can see that as we introduce our copper-based inhibitor, we see signs of interaction, which have hinted to us about the mechanism that's occurring. So what you can see here is we've got good indications that the copper carbonate is becoming a copper 2+, even though the copper carbonate was insoluble and apparently insoluble. And part of this has to do with a copper bidentate formation. So sometimes advanced techniques like the synchrotron help us to demonstrate things like these structures. But what this is allowing us to do is offer a much more targeted view of how we can develop and select and develop inhibitors that actually have a chance at working against a system like MDEA, which I will again say, at least some of this audience is very much in favor of being our future solvent selection. So with that, I recognize that I want to leave a few minutes to answer questions and to discuss. And I know that this was a very high level discussion, but as we come back to this sort of slide, I hope that you have a bit of hope that there is a path forward, particularly as we integrate findings in the lab with the pilot scale, that we can start to drill down and better understand corrosion so we can target it. And then we can use advanced sort of techniques to help us to better identify inhibitors that will be effective. So I think there is a potential for this. And with that, it's been my absolute pleasure to talk to you today. And I would be happy to answer questions now, and I'm more than happy to discuss offline, particularly about any of the electrochemistry, the synchrotron work, etc., the QCM work. So thank you very much. And yeah.
Thank you, Kyra. Just for clarification, you were talking about using the copper inhibitor with carbon steels, was that right?
Yeah, so I realized that I glossed over that. So thank you for asking for the clarification, John. So one of the things that we're focusing on is looking at the role of carbon steel. I think one of the challenges is recognizing where it could be implemented and understanding that it can't be implemented everywhere. The other thing that can be done, which we're also working on, is understanding how stainless steels respond and trying to look for evidence of different types of those localized corrosion phenomena, because I think we need to have a balance of the two. But with a price point for carbon steels that can be something like only 25% of the cost of a stainless steel, like just to give an order of magnitude, it makes a really big difference.
Okay, thanks. So Ian, in McKinley, you had a question.
Yeah, sorry. What is wrong specifically with vanadium environmentally within the context being discussed today?
So vanadium, I think, so this is anecdotally, I mean, I think vanadium is going out of fashion for a wide range of reasons for industry. That's generally the view in terms of industrial use for inhibitors. You know, arsenic was used a lot previously. So arsenic, I think, is a more obvious one to eliminate. But vanadium is certainly, I think a lot of people are looking for alternatives. So I'm not an expert on all the details of vanadium.
Oh, thank you, Kyra. Cheers.
Yeah, my pleasure.
Okay, question from Alex Force.
Hi,
So-
can you hear me?
Yeah.
No, maybe I can try and clarify this question because I don't think I posed it very well. I think it was mentioned I should introduce myself very quickly as well. So I'm a lecturer working on absorbance and also electrochemical carbon capture in chemistry at Cambridge.
Cool.
I could kind of see that with I really enjoyed the talk. So thank you for that. With the tertiary amine, I could sort of see that you had formed the bicarbonate and that could drive the iron carbonate or bicarbonate formation.
Yeah.
With the sort of primary amines, can you speak to like how the amine actually gets involved, and is it being reduced, or what is being reduced?
So I mean, what I would mostly suggest is we have an offline conversation and I can share some other data and some mechanisms and discuss it a bit more. There's a wide range of things that are happening in that particular context, and I have a bit of unpublished data I'd be happy to share with you, and we could actually, we could troll through it if you would really like. But you're absolutely right, is that, we have a wide range of things that are being reduced in the system, and it depends on the pH. We're operating out the loading, things like that. So it's, there isn't a clear-cut answer for every, we need to kind of parse it into lots of bits. So do you want to send me an email and we can arrange a chat?
Yeah, that sounds good. I was going to follow up with you. I was also wondering in terms of online techniques, whether anyone's used things like NMR, because that's our kind of area of speciality here in terms of doing online NMR and solid state NMR and things like that.
So I have a feeling we're gonna have a very long conversation. So nobody uses it online. Mostly FTIR is the furthest that anyone will go online, or electrochemical noise. And I won't comment on the reliability of that as a measurement. But we also do NMR outside the system. So we could talk about this, and I could tell you what we're doing in terms of understanding. That would be very cool. I'd be very happy to talk to somebody else who thinks that that's interesting.
Okay, great. I'll drop you an email. Thanks.
Perfect. Great.
Can you just explain the use of the NMR a little bit, Alex?
Oh, so, well, some of the things that we've done in the past are things like monitoring the speciation of CO2 in adsorbent. So some of these questions like, do you form carbonate, bicarbonate, carbamate, carbamic acid, all of these different things. But with the, I guess with the amines, I was wondering, like, would you see some signals from either oxidized or reduced amines? Have you seen that kind of thing?
Yeah, so we do the same as you. We do mostly carbon 13, and yeah, and a bit of, obviously a bit of per ton. But we mostly focus on similar things like speciation, and we tend to use, but separating carbonate and bicarbonate in the solution system, for example, can be problematic, and has to be done. Well, it doesn't have to be done predictively, but I can tell you where we're at with that and what we know and what we don't know. In terms of, oxidation reduction, there is an interesting scope there actually to look at it. And it's not something we've done yet. Does that help, John?
No, thanks, that helps.
Yeah.
Hubert, you've got a question. A bit rather.
Yeah. Thank you, John. I'd like to start, Kyra, if you don't mind, by saying that in order to come to your seminar, I had to break off a very enjoyable conversation with a good friend of mine called Jeff Mogridge. You may know him.
I do know Jeff. That's really funny.
Once I saw the connection, I sent him an email and a link to this. I don't know if he's taken it up. Well, I might just say Jeff and I were, quote, friendly squash competitors for the last 40 years or something like that. And he's growing a fabulous, fabulous colored garden here in Kings, where I am at the moment.
Oh, amazing.
Yeah, it is amazing. But now what I wanted to ask you is, you explained the physics and chemistry really in an exciting and clear way. But what about the finance? How much would all of this cost? And how much would it cost, do you think, if we didn't do it? Because I've talked about CCS to the European commissioners, and boy, did they think cost was important.
Yeah, so I mean, I would be the first to say, I mean, I think cost in this case is important. And I think that's one of the, I often use the starting point, which is that natural gas sweetening companies make money. So they can afford to buy really, really expensive steel. They can afford to buy really expensive inhibitors. They can afford to do lots of things that in a process like post-combustion capture, we can't afford, right? We're already going to lose money. And so when you're in the red, you need to figure out how to save. And I personally see this as an opportunity to be intelligent and make better choices. So I think that's really where the question comes in, is about where can we make cost savings that do not, we have to make sure that we don't put anyone's health and safety at risk. And so where can we draw that line? And I think that's sort of what I think everyone is thinking about, right? Is where can you start to cheapen the infrastructure materials? Because from a CapEx point of view, the building of these facilities is astronomical. And so if you can reduce that, especially without a big impact on your operational costs and your long-term sort of viability of the plant, it is a really, it is a really complex question. And the comment that often comes up is Boundary Dam uses some cement, and this is true, but they have also encountered problems. So we know that that is not a perfect solution either. So, I don't know the costs. I suspect that probably in, the next iterations of my work, I will probably become more intimately familiar with that. I think for me first is looking at the viability, whether or not we can technically make this happen from a scientific vantage point.
But I think you do have to say something, if possible, about the costs in a quantitative way. That's the only way that you'll get companies and politicians, unfortunately, to listen and think about it.
Yeah, so I think normally we quote something on the order of carbon steel versus stainless steel categorically is around is around a quarter of the cost. So it can sometimes, you know, there's a large error margin on that because there are many types of stainless steel and there are lots of types of carbon steel and different infrastructure. But I think generally most handbooks would give you that as a guide, somewhere between 20 and 30 something percent in terms of the cost comparison. So it's huge. It's a dramatic drop in terms of the impact on the CapEx.
But the question is, that part, how much is that of the total cost? You see, it could be that minuscule cost is twice as large, big deal, that wouldn't matter. But a reasonable cost, twice as large, that could be impossible.
Yeah, no, absolutely. I think that's exactly, you make a very, very valid point. And I think these are really important things. And at the most economic costings are made with assuming stainless steel.
Okay, well,
so that may be something we should discuss, and you can point me in the right directions.
Well, I'd happily discuss it with you. And I was going to say, whatever happens when I see Jeff next, which is likely the next few days, I'll tell him, I'll show off what an enjoyable seminar I've heard.
Thank you so much. Thank you very much.
Okay. Yang, you got a question?
Oh, hello. I have typed my question in the window chat. Can you read?
Yeah, absolutely, Yang. So I did look at your question. So most plants do some type of monitoring. So let's talk about industrial scale. They do monitoring. It would be very unusual to have any industrial process not monitored. The question becomes what type of monitoring and how much. And, you know, there are petrochemical processes, right, where they basically evacuate the entire plant, shut it down and still do a manual in-person inspection. And sometimes that is the only way. There is no great technology to actually look for it better than the human eye. It doesn't mean that's always the solution. And I think what was kind of pointed to in the TNO example was that the location they chose is one of the most egregious generally, and was looking at basically whether or not these monitoring devices really could be adequate. And whether you basically focus in regions and then you assume it probably, you know, that the other regions are less serious. Corrosion is always said, you know, there's always a comment said that there's some stochastic aspects. I'm not sure I like the term stochastic. I believe that it's something we don't know yet. And at some point in the future, we will better understand what we thought to be stochastic. But that said, I think, yes, monitoring is going to be essential. There isn't any way, shape, or form, you know, to get around that. It's going to be impossible. And it's about making that link, making the monitoring useful. And we can't make the monitoring useful unless we connect it to data we've collected in like a pilot facility where we've done comparisons, and we can't connect that back. We need to connect it to the lab where we know that, say you see a spike or a real change in your flue gas composition, we need to understand the impacts that has. So I think a lot more integrated work would actually propel this decision-making a lot faster.
Yeah, okay, thank you. I understand this, the study and the mechanism of corrosion is important. In the meantime, I'm thinking for long-term monitoring, what's really happening to the materials? I mean, pipelines, storage facilities. What happens to them? Yeah, so the biggest challenge is that a lot of the monitoring technologies don't pick up localized corrosion. So you have to, a lot of times you have to do things like manual inspection and similar. The good thing about that, I would say, is that industry has experience doing this. This is one thing that I guess, we can apply a lot of a long-term knowledge from natural gas sweetening so that we can make better decisions in terms of what we need to do for safe monitoring. Yes, indeed. Thank you very much. Thank you.
My pleasure.
Okay, so Kyra, I think we'll just very quickly take a question from Mikhail. Can you see it?
Yeah, I can see it. Okay, so.
Yes, hello.
I can see your question. So no, it's fine. Do you know what? I gave quite a superficial overview, and actually, so my group has worked with lots of different amines, in part because we've looked at including blends, because one of the things we're really interested in is how they interact with metal ions, therefore producing some sort of corrosion product. So I did spend a lot of time talking about MEA, mostly 5 molar MEA, because that's kind of the gold standard. But that's not to say that we haven't done work on other amines, as have other groups. And one of the big things is understanding the differences. And one of the I personally think one of the really cool things is when you have these blends, is which behavior dominates, and understanding how that interaction is happening with the metal ions in solution, and whether or not that acts in a beneficial way or not for you.
Yes, thank you. I was pretty sure that I just missed it during the presentation. And I was also imagining that you did work with the industrial benchmark, shall we say. Plus, perhaps to further that a little bit then. So we are not doomed, as you have said during the middle of your presentation. Well, because corrosion inhibition has been done everywhere and for a long time. As you have just said, natural gas sweetening companies, they earn money. The same can be said for any oil refinery, and they all have corrosion inhibitors.
Yeah. So the difference, I mean, is sort of what I was getting at a little bit with the finance questions, which is that they're all made out of stainless steel. And the challenge we've got is that there's an impetus to try to find alternatives for for building these types of facilities so that it's less expensive. So that's where we've got a challenge. But I mean, you could also make the comment, why are they using very expensive stainless steel and inhibitors, right? If stainless steel is really supposed to be protective. And the answer is because they know, just as any of us can know if you go read the literature, that in fact, the stainless steel is not impervious. As soon as you have a defect or you have a failure, the chromium oxide doesn't work forever. It's not a miracle cure.
Not a panacea, yeah.
So there you go. So even if we go with stainless steel, we still need to be prepared. And one of the big things, even natural gas sweetening, that industry is talking about is removing the use of arsenic, but also removing the use of vanadium, which was the first question.
Yes.
And I don't understand all the logic behind vanadium particularly, but there is a move towards green inhibitors generally anyway. My understanding is there's a lot of logic behind that, ranging from how it's produced, where it's produced, its own life cycle analysis. But there is even a move within that sector to do that. So there is also some nice crossover there.
Great, thank you so much. It was one of the most enjoyable conversations I've ever watched on the UKCCSRC.
Great, thank you so much. I'm really glad I could make corrosion exciting.
I'm pretty sure I'm not the only one who loved it. Thank you.
Thanks.
Thanks, Kyra. Okay, I think we've got to draw to a close there. Vic, do you want to update us on what's happening next?
I would. Thank you very much, John. Firstly, I'd just like to say thank you so much to Kyra for presenting today. Did make corrosion exciting. So just coming up next week, we actually have 2 flexible funded research updates. One is CO2 transportation research on liquefaction of gas mixtures and recovering liquefaction costs, and that's from Kranthi Jonalagada at Cranfield. And we also have post-combustion capture design options for achieving high capture levels, and that one is from Stavros Michaelos at the University of Sheffield. So we hope that some of you will be able to join us again same time next week. But once again, thank you very much to Kyra, and thanks to John for sharing. Thank you all for coming.
Thanks very much, Kyra.
Yeah, it was my pleasure, John. Happy to do it.
Yeah.
Thank you, Kyra.